right, coding session time. I'm excited for this one. I think in the last few sessions we've spent enough time improving, doing quality of life improvements, making the language a bit easier to work with, and it's been super valuable. But I'd like to make some progress forwards with our multi-threading, with our boomstick. Get some gains with that, and I have some ideas of how to do that. So let's get stuck into it. The first thing is that actually I want to change the job that we're doing in every frame. So I found this old commit, and this is where we have an old version of the loop that I'm going to grab. This was back when we were just single threading and everything. And I'm actually going to do this. Might even do it like right up here. We're going to basically do the positioning of all the triangles up here. And then we're going to have a different job that we're going to do during the frames. So I think I'm going to make this, I'm going to do this as indexes. So we also need a triangle count 1D. So I guess this could be just that times that. That's kind of nice. So triangle count 1D, so that's our max. And we can just do a plus equals 1, like so. And buffer data is vec3s now. So we need to do this a bit differently. And instead of this index, I guess we can have a triangle. This is for every triangle, right? So we can have a triangle index, and we can, every iteration of the loops, we can bump that up. And maybe we can just have a vertex index actually. I guess that's essentially what we've got here, right? Except we can have it, no, that was a float index. So this is a vertex index, so we only need to increment once per vertex, and we can take out all these. So that's a bit nicer. So this becomes vertex index. And within each vec3, we have the 3 values, like so, but this x and y are not right. So what should they actually be? It's kind of like this. But we already use x and y, so let's call this left. Come on. It's hard to double click a single letter. Okay, so it's -1 plus triangle size times column count, which is y, or row count, which is x. I don't think that's right. X is the column count. Yeah, y is the row count. Yeah, I think that's right. Let's see. Probably if we get it around the wrong way, it'll probably display right anyway. It probably doesn't make a difference that really in the end. So that should make all of our triangles. And in our task function, let's just cut all that code out and do nothing. And maybe even just comment it out completely, and we should have our triangles. Oh, we need to get rid of our tests because they're too slow, which we will fix one day. One day. Okay, triangle size is not defined. It's true, isn't it? Here's triangle size. Let's do that. There's the triangle size, which is a float. How about that? There we go, lots of triangles. I think we can reduce the amount of triangles for this. There, now we can actually see some triangles. That's kind of nice. They're not so small that we can't see them. Now what I want to do every frame is move those triangles. So if we go data index 0 plus equals 0.001 or something like that. So ideally we would use a delta time or something. We don't actually change that one. Ideally we would have a delta time that we would use in here, and that delta time would allow us to make sure that the speed is consistent, but it's not that important. So let's see, if we just do the single threaded version of that, we just call this function with all of the data every frame, what happens? There we go. But this should be 2. Not that it really matters. But there we go. We get some moving triangles. And how fast are they moving? 80 something frames a second. So it's pretty slow. And that's all right. That's a good starting point, that it's nice and slow. We have something to work on. Okay. What I would like to do is I would like to be able to do, well, I would like to be able to define a vec3 up here that we're going to call delta. So there's a vec3. And we're going to assign these values the same as these. And then I would like to be able to do something like data index plus equals delta. All right? So this is an array, and we can add them together. That's the idea. So let's do a nice naive implementation of that. The naive implementation should be basically evaluate to the same assembly, and performance should be about the same. But let's have it go. So first we need to allow it in type checking, because right now it's going to say that we can't do that. Yeah, we can't add a sign with these vec3s. So we need to allow that to be done. If we type check assignment, there should be some checks. Here we go. So at the moment it's only allowing, if it's not a numerical type, it's going to fail. But we want to say, like, if the type is array, then it's okay, but it's only okay if, so we need to get the element type node. So that's the type of the element within the array, which will be the first child of that node. And if that element type is a float, Well, if it's not a float, or it's not, no, if it's not a float or it's modulo, then we have an error. So we are allowed, if we have an array of something, then we can do some sort of mathematical assignment like plus equals, minus equals, times equals, divide equals, but not this one, and only if it's float. That's the idea. So it should pass type checking now. And we get a generation error, which is fair. I would expect that to happen. Just trying to think if there's anything else we need to do in here. I don't think so. There was, if I just comment that out, there was something I noticed. Yeah, like this stuff here is pointless, really. Well, I don't like how we've got this like this. I'm not sure why that's not taking on any file information. Let's just have a quick look at that. So this is when we are parsing an assignment. Here's our tokens. So we make our node. We don't. File info equals. So we should probably get the whole token. Like that. That's probably what we did wrong. If I do that, there we go. Now we actually have the right. See, now that we have the file information, this is really redundant. It's not really helping us at all. It's just a bit too verbose. So I want to have a look where, so failed to import module. I don't care about that. Failed to tokenize module, I think that's superfluous. So we can just do a simple or return. And failed to type check module, which is what we have here. Like it's already said failed to type check assignment, so it's totally redundant. And I think if we go to type checking, there will be one other place where, yeah, failed to import module. We can get rid of that. It's just a little bit of tidy up I wanted to do. I still want to reduce this as well, like make this a little bit less verbose, but that's good enough for now. And we have a little fix in here. Great. Okay, so now if we go back to here and comment this so that arrays are allowed. So now we need to go into, assignment generation and have a look in here. So this is doing it for different types. So I want to put a new one in here. I'm going to say float array. And this is if we're talking about an array. And because of type checking, we know that if we have an array here, it must be an array of floats. That's the only option. So let's duplicate that and go array. So what do we want to do? The naive approach. I think naive approach is basically to loop through all the floats and cause this, call that. So we need to know the length of the array. There is a get length location, container type node, container location. So I guess it's the, well, we want to do the left-hand side. That's how many we want to copy. We want to base it on the left-hand side because if we base on the right-hand side, we could get overflows and stuff. With the left-hand side, it'll be fine. It might copy some stuff from the right-hand side that's overflowing there, but at least it won't overflow. It won't copy in to somewhere overflowing, if that makes sense. So I think type node container, and because it's an array, we know that this location will be an immediate. So we can just grab the value, which will be a string. So we want to convert it to, no, to I, to an integer. And that should be our integer length. Cool. Now we can do a loop for index equals 0, index is less than length, index plus equals 1. Basically, we can call this. And takes all the same arguments. So the location is what's going to need to change each time. We can change the offset of the location. That only works for memory. But I think for now we can assume that both of them are memory. We're going to change just a different strategy later on anyway. So we'll just assume that for now. I'll do this so that allows us to modify these parameters. If we do this, it's kind of a Odin trick. So we need to know the element size. So the element type node again is the first child of this guy, and the element size is the byte size of that. All right, so let's say element type node. That's what we're, yeah, because we're dealing with just a single element now. And after each one, we'll offset it by the, oh, I spelled that wrong, the size of one element. So to go to the next element and assign the next element. That's the idea. I think that's about it. So this should hopefully do the job. Let's see. That's not actually declaring it. Okay. And it's got about the same frame rate. So that's nice. And if we look at the code, here's task func, which is the right procedure. Oh, it's within the for loop. So here's our assignment. We check the bounds. And here we have our three. This is the first one, second one, third one. We copy the, I believe it's the left-hand side to a register. Then we add the right-hand side to that register. Then we copy it back to the original bit of memory. Cool. Okay, and it's basically the same code that we probably had before. Like if I cut this out, so now we have three assignments. So it's similar. We're doing like more bounds. We have to do more bounds checking because there's bounds checking here and well, not here actually, because this is, well, yeah, probably here and here. So there's like lots of bounds checking going on. So this is already more efficient because it reduces the amount of bounds checking that needs to happen. Only one bounds check pair instead of like 6. So it's better, less instructions. But we can do better than this because these registers, these are SSE registers. They're SIMD registers, single instruction, multiple data. And that means that we can do multiple operations at the same time. with these registers. And we're basically looping through and doing multiple operations. So why don't we do them all at the same time? I'm just going to comment this out for now. And let's see how we go about doing that. It's probably kind of similar to what we do here. So this here is, I think that S stands for scalar. And if we change it to P, don't ask me what it stands for. But when we do add scalar, it means add a single float to a single other float. When we do add P, it means there's 4 floats on the left-hand side, 4 floats on the right-hand side. Add them all together and get 4 results. So we do 4 at the same time. There are other registers which you can do like 8. I don't know how much support for those there are. Like if we relied on those, I don't know if there would be some systems, some computers people still have that would not have those registers and it wouldn't work. Maybe some firmware or something would like emulate them. I have no idea. But we want to do this. So I think as far as the operations themselves go, this is all we have to do. But this copy, we effectively need to copy, like this is just going to copy one float, right? We go copy, copy. See, it doesn't move S, move scalar. So it's just moving one float. We need to give it the ability to move more. So I kind of want the ability to like, well, we want to get the length again, I guess. Where are we? This is not the right place. Here. So some of these things we still want. We want the length. I guess the precision can be made from that. Yeah, we want the length. And I guess we want to pass the length into here to say this is the amount of floats that we want to copy. And the type node should probably be the element type node. Now to simplify things, this might not seem like I'm simplifying it right now, but it'll become apparent soon. When we do this initial copy, I want to round this length up to a multiple of 4. And because remember I said that you can do 4 floats at a time. So let's just round this up and soon we'll see why. I think I have over here, I asked AI how to do it. Was this it? I think it's down the bottom of this chat. Here we go. This is the basic math. So that's like length multiple 4. That's a terrible name. But this math here will basically take length and it'll round it up to the nearest multiple of 4. Like so. This one we're going to have to keep as the length that comes in. In our case, that's 3. And we'll see soon why. So we'll go here, copy to register. And we'll say we can have a count here. I guess for consistency, we'll put it here as well. And not this one, but in the actual copy, we'll have it. And then in here is where we actually need to do some special stuff. that should be fine now. Okay, these other ones, these are places where we have the optional, see the last parameter is an optional comment, and because we put the count first, we need to put that just as a 1. Where else? Here, there, and so I put this here because I didn't think this should ever happen, and we never hit this assert, so I guess it never does happen. So I might just say cannot nullify a non-memory location, something like that. So it assumes this location is memory. Cool, that takes care of that one. Those should sort themselves out. So in the copy here, when we've established it's a float, we need to check the count, I guess. If count is greater than or equal to 4, and I'm going to do another one of these guys so we can modify the count. If count is greater than or equal to 4, what we're going to do is we're going to do a move PS. So again, that's going to move 4 floats from destination to source. And we have said that the count we want to move is 4 or more, so we can do that. Well, I guess we want to loop actually, as long as it's more than 4. And we'll reduce it by 4 each time. Eventually we want to do something better than this, because if we have a really long array and we add to it another really long array, this is going to make our executable get bigger and bigger, because we're going to have a big list of these instructions every time we do an add like that. So we'll probably have to do something smarter at some point, but this is good enough for now. And then as long as there are more after that, we're going to revert to our move scalar. But we have to do something a bit clever. So I guess we don't do this here. We need to do something a bit clever here, because move scalar is going to move it into the left slot. You know, you can think of this, you can think of the XMM register, like XMM0, whatever it is, as having 4 slots for floats. And when we do anything with like move S, or like I was shown before, there's like, yeah, div S, mul S, sub S, all of this stuff is, where were we, down here, is just operating on this A, right? So if we move, we need to minus equal 1. So if we move something into here, say, because our count is 3, right? So we want to fill these 3, but move S always works on this one. So I guess every time we do it, if we need to do another one after, then we're going to need to do, basically what I'm going to do is like a shift. So if we shift everything so that it looks like this, so effectively we shift our A over here, and then next time we do a move S, we can put something here. And then we shift again. A, B, and then we can put our third thing here. And then after that, we're going to need to do 2 more shifts to get back to here, right? So we're going to cycle all the way around. The A goes from here to here, and that means that when it's in this configuration, we can put something into A, then we put it in this configuration, we can put something into B, this configuration, we put something into C. So if we've done one and we see that the count is still greater than 1, greater than 0, then we can do an operation that effectively does this rotation stuff. And I found out what that is in my SIMD chat. Just have to find it. So it's not here. This is it here. Shuff PS. Shuff P, and the S on the end is the precision, which for us is always an S. So it's SS, and then there's a third argument, which is this OX39. And we're only doing this to the destination. Right, we're moving to, no. I guess it depends whether we're talking about memory or register as the source or the destination. Okay, yeah, that is interesting. Let's first just do it in terms of the destination, and we can figure the rest out later, because right now what we're doing is we know that we're copying a 4, an even 4, so it'll just do this and won't come in here. And then we're doing a copy of 3, and that copy of 3 is coming from a register to memory. So actually that means it's the source that we need to shuffle. Okay, we might need to figure this out a bit better. Because we're coming from a register, so we need to rotate this register around so that when we do the move, we're moving from this part here. Okay, so let me explain this OX39. It shows it somewhere down, here it is. So the shuffle control OX39 in binary looks like this. So I think the idea actually is that because this is O1, that means the slot on the left, what I called A, will go into here, the last slot. This is binary for 2. So the B will go here. Is that right? Zero, 1, 2, 3. Like this is just what my intuition was when I looked at this. I thought, well, I guess the binary is saying where to put, which slot to put, like what is the source for this slot? What is the source for this slot? So if the source for this slot is the third one, yeah, if the source is 3, then 3 becomes here. And here the source, no, the source is 2. Oh no, so yeah, the source for this one is 3. So what was in 3 becomes here. the source for this one is 2. So what was in 2? No, I've got it wrong. I'm not actually sure how this works. I'll have to have another think about it. But I think it is something like that. Like we're using it effectively to shift everything to the left and wrap around. But I'm pretty sure this shuffle could do any kind of, if you know about GLSL, if you have a VEC3 in GLSL, you can do something like XYZ. Like this. And then this guy will be the same as this. But I could do ZYX, and that would sort of rearrange the elements of this and store it in this. And this is effectively the kind of thing that you can do with shuffle, I think. You can rearrange all these elements that are in the register in any way that you want. Or, you know, you could even do like XXX, have 3 X's, something like that. Anyway, we're using it to shift things around. So we do some shuffles in the destination, no, in the source. I think this needs a lot of work, but I think that might do the trick. Cannot nullify a non-memory. Interesting, that's what I just changed, right? Oh, because I just put false in there. I'm so used to just having false. So we're asserting that it needs to be memory. Okay, instruction inspector, 1773. Move, actually it's not just move PS. There's a couple of variations. There's move APS, which is for aligned memory. They talk about aligning the memory to at a 16-byte alignment. So that means that our set of 4 integers, the beginning of, no, 4 floats, the beginning of that should be aligned to a 16-byte boundary in our memory. Right now we have no idea what alignment it has. So I must have asked about it somewhere. Yeah, there's this move UPS, which is unaligned. So apparently it can be a bit faster if you use the aligned version. Yeah, what to do? We're not aligned right now. So hopefully that'll fix that. But we get a core dump. So let's have a look at the code. So it looks like we are copying some memory into a register, adding another memory to it, and then this is us moving. Look, this is not good to start with. Because we're moving we're grabbing the first element, then we're shuffling so the second element is ready to take out, but we're putting it in the same place as the first element. So actually, we need to maintain an offset. So this is assuming the source is a plus equals size of one element. And I guess destination dot offset plus equals size. So I guess right now that's all we need to do. Let's try that. Okay, destination is also, so let's, I think this time we might, because we're gonna, I don't know why I didn't feel like doing that with the other stuff, but let's make a copy and use the copy as our destination. And that copy we should be able to modify. We still have an error. So at least now we have +4 +8. So the second and third element are going to the right place in memory. This is when this part is us copying the result. So we do the add, so the result is in here. And this part is us copying the 3 elements out. This is why we needed to make sure in here, when we're doing the operation, that this final copy has the length, not this length multiple 4 business, because otherwise we would copy 4 elements into this destination, but that would overflow into some other memory because this destination only has space for 3. Whereas on the way in, like when we do this, when we're copying into one of these registers, it doesn't matter if we copy the 3 things that we know here plus some random memory, because we don't really care that there's going to be some random memory at the end of this. It'll end up doing an add of some random jumbled up memory at the end of the register, but we don't really care. I'm kind of wondering whether this is allowed, having memory on here. So let's try. I think when I played with this before that I didn't like that. So if we make an RHS register location from RHS, we'll use a new register. And we'll copy from, we add from there. Hey, they are moving faster. See, look at that. That's like double. I think that's like double the FPS we were getting before with this here. So we copy our 2 operands into registers, add the registers together, and this is us copying the result back out. Cool. Okay. I would like to make this a more kind of general solution, because I feel like right now it handles our current solution, but not great. So this is considering the destination as memory. So, well, I guess this is, while count is 0. Let's wrap this in a count greater than 0. I think we can get rid of this. This was for demonstration purposes. But yeah, it was just like, we copy the element on the left-hand side of this register into here. Then we shuffle the elements around so that when we copy the left-hand side one to here, it's actually the second element that was originally there. Okay. So I want to do something like if we're copying from memory, and let's keep track of the offset. Something like that. So if we're copying from memory and the offset is greater than 0, we want to do a shuffle. So that means we're copying from memory and we've already copied the first part because we've produced an offset. So we want to shuffle the source now. Yeah, we're going to shuffle the source. We're doing a move scalar. And what happens if we're copying from memory? Then we want to offset it. Yeah. And if we're copying I guess we want something very similar here. So if the destination is memory, then we want to shuffle the destination. And we want to, and if it's not memory, if it's a register, we want to offset. And it doesn't matter, like if we come in here when it is memory, but offset is 0, we'll offset as 0, so it's not going to do anything. And we go from source copy to desk copy. And then we decrement our count and increment our offset. I think that will still work, but it's kind of a bit more general purpose. Apparently it will not work. Because we're doing R11, R11. Whoa. Oh, I must have run out of battery in my light. Should have kept that plugged in. Where are we? 48 minutes. I think we're doing all right. There's a little bit more I want to try, but I'm sure we can get to it. So the shuffle, if the destination is memory, we don't want to shuffle memory. I think I got this run the wrong way. If it's a register, then we want to shuffle it. There we go. So it'll need some more rigorous, it'll need some more rigorous testing, but it works so far. And so we can see our frame rate is, yeah, maybe at 200. Oh yeah, it looks like we're getting a bit above 200, 250 even. Okay, let's see if we can get that a little bit higher, because we have these nice fast operations here, and then we have this shuffling around business. What if we can avoid this? So the way to avoid that could be if we change to a VEC4, and here, not in that code. but here we can change to a vec4. Here we can change to a vec4 like that. And so that OpenGL has enough, allocates enough memory, we need to make the buffer a bit bigger to handle so that we have 4 floats per position. And we need to tell it that we have some spacing. So we're telling it that we're storing 3 floats. And because this is the stride, because the stride we're saying is 0, it means that there are 3 floats per attribute and they are tightly packed. But now we have a bit of space in between, so we manually say that we have 16 bytes per attribute. And now we should, instead of this, just get like a regular move UPS. What? Okay, I thought that was going to be better. I thought that was going to make a difference, but it doesn't really. Doesn't make that much difference, actually. Okay, I thought that would be better. If it doesn't make that much of a difference, then I think it's clearer just to leave it as a vec3. Like so. Okay, but we've managed to squeeze, you know, like more than double out of this already. And if we go back to multi-threading, so let's go back to not using SSC. Where were we at? It was like 80 frames or something. Yeah, 70, 80. But if we multi-thread it, use our boomstick, that should pick up quite a bit. For 400, that's nice. But what if we also use our SIMD? Wow, it's gone. 15, 14, 13. That's looking pretty good. There are some other things in our thread pool which are not great. And I thought we might improve. We've got these spins. So this is basically like a thread is just like being used, waiting here. So I thought instead of that, if our thread pool can have like this working variable inside of it, and we can use that along with this futex stuff. So this is a futex wait. So thread pool wait would just become a futex wait on pool dot working, and it's expecting 1. So I believe that means it's only actually going to wait if pool working is 1. So whenever we add a task, we can say the pool is working. And then when a worker finishes, if a worker finishes and it's the last worker to finish and there's nothing more, no more tasks to grab, then we can do the futex wake. Where was it? Here. With the pool.working. Oh, well, I guess we need to say pool.working equals 0. I don't think the value of it matters when we do this wake. We're just saying anyone that was waiting on it can be woken. And we don't want to just wake one, we want to wake like all of them. And ideally, I would like to be able to do something like i64.max. I'd like to have that in my language, so we could just put that here and just so it'd be like as many as possible could be woken. But just putting a big number here, I think will work. So if working is 1, which means that we have added something to the pool, then this should wait for it. And when we have finished working, so this is the last worker that was doing work, and there's no more work to be done, then we say, hey, everybody wake up. Anybody that was waiting for the thread pool, you need wait no longer. Let's see what happens. Okay, I think we're getting like a little bit faster on some frames. But nice to see that it's still working, and that means that when we have, well, I guess this was only one thread, right? It was the main thread here. So there's one thread that wasn't doing anything, that was not doing anything before, and now, or one core that can be freed up to do something else. Another thing where we were just spinning was the semaphore, when we wait for the semaphore. So I also want to do like something like this. So the idea being that when we're waiting, we try to decrement the semaphore. If we were successful, if it didn't go negative, then we're done. Otherwise, we undo our decrement and we wait to be told that there's another chance to do it, instead of just trying over and over and over again. So that'll mean that this is also not using up a core. It does mean that we're going to need a type. Semaphore equals struct. So we can say value, which is the atomic I32. And I guess we'll just call it waiter. I don't know. Doesn't really matter what it's called. I'll just put an underscore T, so it's the type. So it's the value that we're dealing with here, and this is the waiter. I think we need to pass in a pointer, right, to futex. Yeah. So it'll wait. We'll put 0 as expected. We never need to change this value. Like if we come here, we need to wait. That's basically it. We just need to wait. And in signal, we do need to increment, but then we also need to notify these waiters that there's a chance to wake up. In this case, we only want to notify one of them, because only one of them can wake up. So it'll be like that. So that should also help prevent us from just having cores that are not doing anything useful. Just spin in. So pool of semaphore should be a semaphore underscore T. There we go. And that's looking pretty good. Okay. So we squeezed a fair bit more performance out of that using the SIMD. And we didn't really see gains with this. I wonder what happens if we try to increase this guy so we have more workers. Okay. Wow, yeah. If we got to 16. My laptop if I go to resources, it says that it has 16 CPUs. You know, it's got 8 cores with the hyper-threading, whatever you call it. So I'm skeptical that you're going to get like double the performance for using 16, but yeah, see, that's not really better. So I don't know what the optimal number is actually. It seemed like 12 is doing better. But it's hard to say, really. Hard to say. Yeah, I don't know. That's something to experiment with, I guess. So let's take this out. And this is just like tidier, right? This is what you would want to do. I think that's a nice thing. Okay, I should give Odin credit for this. Odin has this feature and I stole it. But the nice thing is, like, this is what you would want to do when you're coding, because it's a nicer code. But it happens to just also be faster. That's really nice. Was there anything else that we wanted to, like, it's been an hour, but just something quick? No, I mean, I'm tempted to do separate files, but I think we're just going to leave it at that. It's getting a little bit late for me. So I think, I mean, I think that's pretty awesome that we squeezed a bunch more performance out of this thing. Like if we have the multi-threading, just want to do some more tests. We have the multi-threading with the old style. Yeah, we get like 600 something. And the new style kind of like, it doubles. So look how fast they go. Yeah, see, it's really like, it's a bit hard to benchmark. You know, I'm getting different numbers all the time, but just with 8, I'm getting these good numbers. Sometimes if I restart my laptop, then I get even better numbers. So I don't know, but I'm quite happy with that. I think soon we should move on to making Boomstick work for the GPU. That's going to be a big one. I'm going to have to do a bunch of investigation because I don't know how to make that work, but I mean, ideally I would just like to be able to do that, and then it will run it on the GPU. You would also need to make sure that this data is in VRAM, which actually for us, it is in VRAM because we used OpenGL to allocate it. Yeah, let's see. Now that I think about that, I'm not sure if we can, because I'm thinking to use OpenCL, which is another library, to run this on the GPU. But I'm not sure if that's going to accept data allocated by OpenGL. Let's see. Let's see if that's possible. But thanks for stopping by. I hope you enjoyed. I hope you liked seeing number go up. I definitely like seeing number go up. I love performance stuff. I love seeing the gains. Yeah, ciao for now.